Root mean square speed. In this podcast, we'll discuss what the root mean square speed is, or the RMS. We'll understand how to read and draw the graphs of molecular speed distributions, and then we'll solve problems using this information. Now, I want to draw your attention to something that I actually sort of glazed over in the previous video. I wrote kinetic energy, but when I wrote kinetic energy, I wrote 1/2 m with this u line over it squared instead of v squared. And I didn't really mention what I was talking about there. Let's actually look at this a bit closer. So this is the average molecular speed. Notice it's not the same thing as velocity, because where velocity is talking about the actual speed with direction of one particular molecule, this is talking about the average speed over all of the molecules in a sample. So the molecules aren't all going to be traveling at the same speed. There's a distribution. So before I show you the graphs of the molecular speeds, I thought I'd show you something else a minute, because this is the distribution graph that everybody recognizes after they've been in college for more than about one midterm. So you're used to looking at these grade distributions that you get off Triple E, right? And many of your classes release them, some don't. So when we look at these, think about what we're actually seeing. We're seeing, well, how many students got a 55 on the exam? Oh, okay, about 36-ish got a 55 on the exam. Well, how many got a 70 on the exam? Oh, okay, well, about 42, 43 got that on the exam. So you can walk through and you can see, well, what, this being, in this case, the grade, this being how many students have that particular grade. This isn't all that different than when we start talking about molecular speeds. So when we start talking about molecular speeds, what we'll see is, okay, we have a certain number of now gas molecules, and for a graph like this, a particular amount of them have this speed. A particular amount have this speed. A particular amount have that speed. And this exact same principles apply. This would be the speed. This would be how many molecules have that speed. And a lot of times what you'll actually see that y-axis labeled as is a percentage. So let's look at this a bit closer with some more labels, a little bit more specific example. So here I have the molecular speed. Again, over here, number of particles. We don't need to know exactly how many particles it is because we're doing some level of comparison here. And we can see here that we've talked about temperature affecting molecular speed, and what we've always said is, oh, temperature, if you raise the temperature, your particles move faster. But now we have the graphs to actually quantify that. So we look at this graph and we see this 100 Kelvin. Now, something that people tend to get confused, notice that the peak is higher, but all that really means is that the graph is squished inward a little bit because everything is slower. And so your average molecular speed is much slower, and your distribution is what we call much narrower. The graph is narrower from here to here than something like 700 Kelvin. So all of these would be representing the same number of particles. If you were to take the integral of all of them, they would be the same. But this has a much higher peak because there's much fewer speeds that those particles are able to possibly be. Now if I raise the temperature, notice that this peak shifts to the right. So now the place where most of the particles are, instead of having a speed of, let's say, 250 meters per second, the vast majority of the particles have a speed around 400 meters per second. And then of course, you still get that distribution. So even though most of the particles are around 400 meters per second, some are still going to be at 2. Some are still going to be at 1, or 100 I should say. Some are still going to be at 700. And again, if you raise the temperature to 700 Kelvin, you stretch the graph out even more, you have an even wider distribution, and because there's more speeds that those molecules may be, you'll see that this peak drops down. But when you're looking at what it does to your average speed, what you're really looking at is your x-axis. And you can see that it shifts quite a bit to the right, meaning that most of your particles, this peak of where all most of your particles is at 700 meters per second. Now let's look at the other thing that can affect your molecular speeds. So here I have one temperature, so all of these are at 300 Kelvin, but I have 3 different gases. So helium, very light. And we've talked about how light things are faster and the heavier things are slower. This isn't much, this graph just quantifies that for you. So here we have this light helium. It's quite fast. And so if you look at where its peak is at, over 1,000, 1,100, maybe 1,200. You look at nitrogen, its peak is around 500. So most of its particles are at 500. Chlorine, most are at 250. So the lighter you get, the faster you get. And again, just like before, even though this peak is lower, that's just because helium has more possible speeds that it can sample, and so its distribution is wider. It's just a stretched out graph. But you're looking at where the majority of the particles are according to the x-axis. So quick summary, when we raise the temperature, we can watch our peak and our whole distribution move outward. So since everything is being stretched out, as we raise our temperature, we raise our average molecular speed. If we keep things at a solid or at one temperature and just look at what happens to molecular mass, we can see that if we go from chlorine to nitrogen, we've gotten much lighter, and therefore our average molecular speed has increased. Our graph has shifted outward or further along the x-axis. And if we go even lighter to helium, shifts even further, giving us an even higher average molecular speed. Now let's talk about this in a little bit more mathematical terms. So according to kinetic molecular theory of gases, I'm going to introduce you to a new equation. So our kinetic energy will be 3/2 RT, and that's per mole. There's a derivation of how this comes about in your book, and you're welcome to look at it if you'd like. I'm not going to hold you responsible for this particular derivation. Now, we also know that the kinetic energy of one atom is 1/2 mv squared. So what would be nice is if we can say, well, what would the kinetic energy of a mole of atoms be? And then set it equal to this. Well, if we think about it, if this would be the kinetic energy of one atom, we would know that the kinetic energy of 10 atoms, we would just multiply by 10, right? So given that same logic, we would know that if we wanted to know the kinetic energy of a mole, we would just multiply by Avogadro's number. So then we would have Avogadro's number equals 1/2 times the molecular mass times the average velocity. So this gives us the kinetic energy of a mole. This gives us the kinetic energy of a mole. We can set these equal to each other. So here I have Avogadro's number times the 1/2 and the root mean square speed, and then the 3/2 RT. So now we can solve this for the URMS, and we get this equation out of it, square root of 3RT over m, where m is the molecular mass. You'll notice in your book they make this kind of a curly, fancy, italicized m. Here I'm just going to leave it as m, and you need to know that that's molecular mass. What does this mean about speed versus mass? So we'll look at where m is. If we increase m, what happens to this whole term? Well, if we increase the denominator, this whole term gets smaller, meaning this whole term gets smaller, meaning URMS gets smaller. So as something gains mass, it loses speed. So in other words, it's inversely proportional. Now let's do an interesting little problem where we can calculate the root mean square speed of a couple of different atoms, and then also discuss how this might have something to do with our atmospheres. So I say calculate the RMS of helium and nitrogen molecules, and then relate this to our atmospheric makeup. So we have our RMS speed equation. So let's do this for helium. We know our 3. Now notice what we use for R here. Be careful. We're looking for speed, and so we have to have that meters per second being in our units. So we can't use the 0.0821 version of the ideal gas constant because that doesn't have the correct units. So we need to use the 8.31 version. We make sure that we use Kelvin as our temperature. Now, I didn't give us a temperature here, so that just means I would care about it at one particular temperature. So I picked 298, room temperature, typical temperature to be around. And then we put in our mass. So for helium, that's 4. Now, notice I had to convert this to kilograms because joules has a kilograms in it. So from here, we type into the calculator, we get our answer, and we know our speed of helium. Now we can do the same thing for nitrogen. We plug everything into our equation, remembering to use Kelvin, remembering to use our joules per Kelvin mole, and remembering to convert this to kilograms per mole, not the grams per mole that's on the table. We get our answer, and we end up with 515 meters per second. Now let's think about this last part. So we maybe know, maybe don't know that our atmosphere is mostly made up of nitrogen as compared to a very, very small amount of helium. So why does that make sense according to this? Well, we look at these speeds and we can see that helium is way faster. Now, to escape gravity in our atmosphere and all the things that are holding atoms on Earth, there's got to be a certain velocity. Which of these two are more likely to have that escape velocity, given any particular temperature? Well, no matter what temperature we use, helium's always going to be faster than nitrogen if they're at the same temperature. And so since this is much, much closer to the escape velocity needed, helium is able to escape Earth's gravity fairly easy. A large distribution, or a large portion of this distribution, will be over the escape velocity needed. Now, if we look at our nitrogen, that's very slow. And so very few particles of very few molecules of nitrogen are going to have that escape velocity. And so therefore, most of the helium escapes, most of the nitrogen doesn't. And it makes sense that our atmosphere has significantly more nitrogen than helium. Helium is faster, more likely to escape, leaving a higher percentage of nitrogen in our air, even if we had started with the exact same amount of both. So in summary, we learned what root mean square speed is. We now hopefully understand how to read and draw the graphs of the molecular speed distributions, and then be able to solve problems using the root mean square speed and the new equation that we introduced in for kinetic energy of gases.